Okay, so simple addition. It sounds pretty basic, right? Like 3 plus 5, we all know that. But it's actually way more complicated than you think when you start to look at how kids learn to do it.
Right. Yeah.
It's kind of amazing. And actually, for, decades, educational psychologists have been asking these really basic questions about it. Like, how do children's strategies for addition change over time? Like, what makes them pick one way of doing it over another? How's their memory organized for these math facts so they can retrieve them so fast? And, even what is becoming faster even tell us about things like consciousness and effort when we're doing these problems.
I think what's really interesting is that for us as adults, we just know 3 plus 5 is 8, right? Like we don't even have to think about it. But that actually comes from a huge developmental process. It's not just memorizing a bunch of facts.
Exactly.
It's really about building a whole system in the brain.
Yeah, it's a journey to get to that point. And that's exactly what we're going to be diving into today. So today's deep dive, forget your timed math tests, those things that we all maybe had to suffer through in elementary school. We're going to be looking at a whole bunch of different research studies where scientists actually watched kids solve addition problems, listened to how they explain their answers, and even measured like how long it takes them to respond, all to try to figure out what's happening in the brain as kids are learning simple addition. So really our goal in this deep dive is to try to map out that whole course, right?
Yeah.
From those first kind of clumsy, attempts to count everything out to that smooth instant retrieval that you were talking about.
Right. And I think to guide our exploration, what we're going to do is we're first going to look at how the strategies children use for addition actually change over time. And this is this idea of a moving on process. Then we'll look at what reaction times can tell us about how these addition facts are stored and retrieved from memory. And there's this really interesting phenomenon called the problem size effect that we'll talk about.
Okay.
And then finally, we'll try to bring these two perspectives together to get a fuller understanding of what's happening. And then finally, we'll touch on this often misunderstood concept of automaticity.
So let's start with those early days of learning addition.
Mm.
One of the things that research has found is that kids actually use a whole bunch of different strategies, even for the same addition problem.
Right, right.
It's not just this nice, neat progression.
Yeah, and early research that just involved observing children and asking them how they solve these problems really highlighted how much variability there is in this.
Yeah. And Dick Svensson and his colleagues back in 76, what they did was they had kids solve addition problems and then explain how they got the answer.
Right.
And what they found was that there was a ton of variation in how kids were doing it, even with the same problem. So some kids, might stick with one method almost all the time, while others, were flipping between different ways of getting to the answer. And actually what's really interesting is that they found that what are called reconstructed answers, meaning that the kids didn't just pull the answer from memory, but they seemed to be working it out each time. They found those were actually more common than just retrieval answers, answers that seemed to be, just remembered instantly.
That is really surprising.
Yeah, isn't it? And another thing is that good old counting by ones was a super common strategy.
Yeah.
Like even for, something like 3 plus 5, kids would count it out one by one.
Mm.
So basically what Svensson's work tells us is that there's a ton of variation in how kids are learning addition. Some stick to one method, others are kind of jumping around. And surprisingly, they're often not just remembering the answer, they're figuring it out each time.
Yeah. And I think one of the things that's really important to think about, for people listening is that this really highlights how learning isn't a one-size-fits-all process. Even for something as basic as addition, everyone's kind of going on their own unique journey, and you can really see that at these early stages.
Absolutely, yeah. And what's also interesting is that Svensson found that kids who used a wider range of strategies for the same problem, they actually tended to make more errors,
Oh, interesting.
which, that might suggest that the challenge isn't just in doing the calculation itself, but also in picking the right way to do it in the first place.
Right. So there's that added layer of complexity there.
Exactly, yeah. And they even found some really, individual kind of unique approaches like a nines strategy. So some kids were, to add 9, they would first add 10 and then subtract 1. So, if there was like 6 plus 9, they would do 6 plus 10 is 16 minus 1 is 15.
Oh, wow.
So it shows you how, kids can be really creative in how they approach these problems,
Yeah.
even if it's not always the most efficient way.
Right, right. I love seeing those kinds of strategies.
Yeah. Then you have Fuson's work in 82, and she really focused on how children are actually keeping track when they're counting, right? So they're using their fingers, actual objects, or even just mental images like picturing dots in their head.
Right.
And she was able to really break down this transition from what's called counting all, where you're counting every single item, to counting on, where you start with one of the numbers and then count it from there.
Right, right.
And she even pointed out this common error that happens when kids are making that shift to counting on. So they'll say the first number out loud and then start counting from there, which means they accidentally include that first number in their count.
Oh, we say.
So for 5 plus 3, they'll say 5, 6, 7.
Oh, yeah.
Get the wrong answer of 7.
Right?
Yeah, it's really subtle, but it really shows you, these little changes in strategy can be quite tricky to get right. And what's interesting, even Fuson found that adults can make similar mistakes when they're doing really novel symbolic addition problems, like using letters instead of numbers.
Oh, wow.
So it shows you that even for us, when we're outside of our comfort zone, we might fall back on those more basic and sometimes error-prone strategies.
Yeah. Yeah, that makes sense.
Yeah. Then you have Carpenter and Moser, and their longitudinal study. They followed kids for 3 years, starting in first grade, and they really backed up this idea that there's this gradual move from counting all to counting on. What's interesting is that they saw kids using both strategies, sometimes even at the same time. And they even saw kids go back to counting all, even after they'd shown that they could use counting on. So it's like they had the more efficient tool, but they weren't always using it.
Right. Yeah, and that makes me think of, even for us as adults, like when we have, multiple apps on our phone that do similar things, like we might know there's a faster one, but we just instinctively reach for the one we're used to, even if it takes a little bit longer.
Exactly, yeah. It's that habit. It takes a while to really switch over fully. And then you have Siegler and Jenkins in '89, and they used what's called a microgenetic approach. And what they basically did was they really zoomed in and watched the learning process unfold in detail over a short period. It's almost like watching a flower blooming and fast forward.
I like that analogy.
Yeah, and what they did was they identified 5 different strategies. Guessing, what they called long sum, which is counting all with fingers. Sum, which is counting all from one. Min, which is counting from the larger number. And then retrieval. And they basically proposed that that's the typical order in which kids start using those methods.
Okay.
And their work really highlighted, again, this idea of using multiple strategies, even for the same problem. So they found that even after kids figured out a more efficient strategy, like Min, they would still sometimes use the less efficient ones.
Oh, so even when they know the better strategy, they don't always use it.
Exactly. Yeah. It's like these different strategies are all kind of active in their mind, and they're all competing to be the one that gets used.
That's fascinating.
And that leads to this really important question, which is, what makes a child pick one strategy over another at any given time?
Right. Yeah, that's a great question. And I think, early on, people thought that maybe kids were consciously weighing the options and trying to pick the one that was fastest or most accurate. But I think that's assuming that kids have like this really good understanding of their own thinking processes, which is probably not the case.
Yeah, it seems a little too metacognitive.
Right. I think more recent models suggest it's a little bit more automatic than that.
Yeah, tell me about some of these models.
Okay, well, so Siegler's distribution of associations model, for instance, suggests that choosing a strategy isn't really a deliberate decision. Instead, it's based on the strength of the connections in memory between the problem and the possible answers, both the correct and incorrect answers.
So it's like a network.
Yeah, exactly. It's like a network in their brain. And these connections, they get stronger over time, depending on how often they've seen the problem and whether they've solved it correctly. There's even this idea of a confidence criterion for retrieval. So if the link to an answer isn't strong enough, a child might fall back on a different strategy they feel more sure about. So yeah, it's really like, some pathways are stronger than others, and those are more likely to be activated.
Yeah, that makes sense. And then you have the Adaptive Strategy Choice Model, or ASCM, which basically says that the strength of a strategy isn't just about how accurate it is, but also how quickly it can be executed.
Oh, right. Okay.
So the idea is that a kid is more likely to use a strategy that's both accurate and fast.
Right. That makes sense.
And this model also takes into account how practice helps learning. So as a kid uses a strategy more, it becomes faster and less error-prone, which then, increases its strength in this kind of mental competition.
Right, yeah. And then I know there's also SCABS, which stands for Strategy Choice and Discovery Simulation, which kind of sounds like it's trying to put all of those pieces together.
Exactly, yeah. SCADS is a more, comprehensive model that tries to explain not just how kids choose between strategies they already know, but also how they discover new ones. And so it includes things like what they call an attentional spotlight, which helps them notice new possibilities,
Mm.
and strategy heuristics that they can use to kind of tweak existing strategies. And also, it includes what they call goal sketch filters, which help them figure out if a new strategy is even appropriate for the problem they're trying to solve. And one of the interesting things that came out of that SCADS model was that they saw the sum strategy, that counting all from one, that emerged as a kind of stepping stone to the more efficient min strategy.
Oh, okay.
So it kind of suggests that, there's this natural progression where kids try out different things, and eventually they kind of stumble upon those more efficient strategies.
So there are all these different ideas about how kids pick the strategies they use, from conscious decisions to strength of connections in their brain. But I guess the question is, how do all those pieces fit together as kids actually learn addition?
Right, yeah.
Yeah.
And the important thing is that it's not like kids learn one strategy, master it, and then move on to the next one, kind of abandoning the old one completely.
Right, right.
And Siegler actually has this nice analogy of overlapping waves to explain this moving on process. So basically the idea is you have these different strategies, the less efficient counting methods, you have the more efficient ones like counting on, and then eventually retrieval and decomposition, and they're all kind of active and competing.
Okay.
And over time, the wave that represents retrieval that gets bigger and becomes the most dominant one, but the other waves don't necessarily disappear completely.
Oh,
So
okay.
it's almost like, you're learning to surf and you're trying out different boards and different techniques, but you're not necessarily getting rid of all the old ones.
Right, right.
Yeah. And I think it's actually kind of comforting. Even when we think about learning as adults,
Yeah.
it's okay to, fall back on those older, less efficient methods sometimes because that wave might still be there, even if it's smaller.
Right. I totally agree.
Okay, so we've talked about how kids' approaches to addition change over time. Now let's look at what we can learn by looking at how long it takes them to solve a problem.
Okay.
So reaction times.
Yeah, reaction times.
And this is the second big way that researchers have studied addition. And it's based on this idea that, the amount of time it takes us to solve a simple addition problem can actually give us clues about what's happening in our minds, especially in terms of how we're using our memory.
Right.
So reaction time is basically just the amount of time between when you see the problem and when you say the answer.
Okay.
And early research in this area was really trying to use these mathematical formulas to predict those reaction times and kind of figure out which strategies kids were most likely using. So like Gruen and Parkman back in '72, they actually came up with this prediction equation where they thought that reaction time was made up of like a basic amount of time plus an extra bit of time that depended on, something about the problem itself. And in their case, they were looking at the number of steps that would be involved in different counting strategies. So like, how many counts would you need for the sum strategy or for counting from the first number or for the min strategy? And they tested this with first graders. And what they found was that the min variable, so the number of counts you'd need if you're using the min strategy, that actually lined up pretty well with the children's reaction time data. So it suggested that a lot of those first graders were using the min strategy. But they also noted something interesting, which is that these tie problems, like 2 plus 2, were solved way faster, almost like they were just known instantly. And so they actually tweaked their formula to account for that, and then it fit the data even better. And what's also interesting is that they found a similar pattern in adults, where bigger problems took longer to answer, but they thought that for adults, it was probably more of a memory search process rather than actual counting.
Oh, that makes sense.
So it's like, as we get older, the process behind those slower reaction times might actually be different.
Yeah. So we're not necessarily counting in our head. It's more like we're searching through our memory.
Exactly, yeah. And then you have Ashcraft and Battaglia in '78, and they were focusing on adults doing addition verification tasks.
No.
So they were showing them a problem and an answer, and the adults just had to say if it was right or wrong.
Okay.
And they found that the square of the sum, what they call the sum-to variable, was a really good predictor of how long it took the adults to respond. And this actually led them to propose this idea that our memory for addition facts is organized like a network, almost like a mental addition table. So in this view, that problem size effect, where bigger problems take longer, it was reflecting how far you had to search in that mental table. And just like Gruen and Parkman, they also saw those faster reaction times for the tie problem.
Oh, interesting.
Yeah, and then Ashcraft and Fearman actually followed up on this by looking at kids in different grades to see when this shift from counting to retrieval might be happening. So in 82, they tested third, fourth, and sixth graders. And they found that for the third graders, a measure of how big the answer was, like whether it was 1 or 2 digits, that was actually the best predictor.
Yeah.
But no one variable, perfectly explained their data. And then for the older kids, that sum 2 variable became a better predictor, suggesting that they were relying more on that network-based retrieval.
Okay.
So they saw third grade as this kind of transition point where some kids were still counting a lot, while others were starting to depend more on just remembering the answers. And then Goldman and colleagues actually looked at how practicing addition changed the reaction times and the strategies the kids were using. So in 89, they looked at third and fourth graders and had them practice addition problems for 3 months, and they measured how their reaction times changed. And they found that as kids got faster overall, the pattern of their reaction times suggested that they were moving away from using counting for the smaller problems, and they were retrieving those answers directly from memory. However, the larger problems still seemed to be solved using counting. So this whole line of research really points to this consistent finding, which is that bigger addition problems just take longer to solve, even when it feels like we're just pulling that answer straight from memory.
Right, right.
And this is what's called the problem size effect. And this has really sparked a lot of discussion and debate in the field, because the question is, why should 9 plus 4 take longer than 5 plus 4 if we're just memorizing both of those facts?
Right, exactly. Like, why should it matter?
Yeah.
And I think that question has really led to a lot of interesting theoretical work, trying to figure out, well, what's going on in our minds that's causing that?
Yeah, so let's get into some of those explanations. We've got, structural explanations, strength explanations, interference explanations. It's like trying to map out the architecture of how we do math in our heads.
Yeah, it is.
So start us off with some of those different explanations.
Okay, well, structural explanations, and these were the ones that were initially proposed by Ashcraft, suggest that reaction time is directly related to what they call search distance. So it's like, if you think about that mental addition table that we were talking about before, the larger problems were thought to be located further away or in a less accessible part of the network. So it's kind of like if you have a big library and you have to go find a specific book, it's going to take you longer if that book is, way in the back corner of the library versus right up front.
Right.
But then strength explanations came along and they focus more on, how often we encounter and use these different math facts. So they argue that the problem size effect is really just reflecting how strong the connection is between a problem and its answer in memory. And that strength comes from repeated practice, so the smaller problems, we see them more, we use them more, so they have those stronger links, and they're retrieved faster.
Okay, yeah, so it's like the well-worn path.
Exactly. And Ashcraft himself later kind of leaned more towards this view, and he talked about how distance is really more of a metaphor. It's not like a literal physical distance in the brain, but it's more about how easily that answer comes to mind.
Okay.
And then we have interference explanations, which say that the time it takes to retrieve an answer is also influenced by interference from other related but incorrect facts that are getting activated at the same time. So for instance, when you see 3 plus 5, your brain might briefly also activate the answer to 3 times 5.
Yeah.
Yeah, and they argue that, again, those smaller numbers, they have stronger associations, and they're less susceptible to this kind of interference because we've practiced them more and we learned them earlier. And then Siegler's strategy choice model also provides a perspective on the problem size effect. And it ties back to those different strategies that children are using.
Right.
So he argues that the problem size effect is not just about how quickly we can retrieve a fact. It's also partly because we might be using counting strategies on those larger problems, especially if they're less familiar or less practiced, or if we're just not as confident in our memory for that particular problem. And then finally, we have Baruti, who brings in this idea of schema-based learning, which really emphasizes the role of understanding the underlying mathematical principles.
Right.
So he's arguing against the idea that adult performance is purely based on just retrieval of memorized facts. And he points out that our knowledge of rules and shortcuts and principles, that plays a huge role in how we solve problems. So he proposes that the problem size effect might be reflecting how well that deeper procedural knowledge has been learned and has become automated, rather than just the strength of, that direct link between a problem and its answer.
Yeah, so it's not just memorizing a bunch of facts.
Right.
It's also about understanding, the structure of the number system.
Exactly. And he gives the example of, knowing the rule for adding 0 or adding 1. Those are pieces of procedural knowledge that really help us to solve problems efficiently.
Okay, so it sounds like there's not one clear winner when it comes to explaining the problem size effect.
That's right. And I think over time, the field has kind of moved away from those purely structural views towards more complex explanations that consider both the strength of the connections and the role of interference. And, there's research like by Zia Brodoff that manipulated how often people saw certain problems and how similar those problems were to other problems. And what they found was that, both strength and interference seemed to contribute to this effect. And I think there is general agreement that, relying on long-term memory retrieval, whether that retrieval is organized around the operands or the numbers themselves, or if it's organized around the problem, that does seem to play a key role.
Right.
And then, Berrudi's idea with that emphasis on this deeper procedural knowledge, I think that's a really interesting perspective as well, because it kind of gets at these strategies that might be somewhere between just counting and direct retrieval, like breaking down a problem into smaller parts. So it's not always just one or the other. And, there's still this debate about how to really distinguish between a strategy that's become so well practiced and automatic that it feels like retrieval versus actual instant memory recall. And, Logan's research, where he found that people actually invented new strategies while they were practicing a certain kind of math problem, that kind of hints at these like in-between stages. So ultimately, I don't think there's one single explanation that has all the answers. But combining the ideas of strength and interference, that seems to give us the most complete picture.
Okay.
And, if we can really understand how those well-practiced procedures differ from just retrieval, then Berrudi's view can offer some really important insights into how those flexible strategies develop.
So we've talked about how kids' strategies for addition change. We've talked about what reaction times can tell us about how those math facts are stored in memory. But it sounds like if we only look at one of those things, we might not be getting the whole story.
That's right, yeah. And I think if we just watch what kids do and we listen to their explanations, we might miss those subtle differences in how quickly they can answer that reaction times can reveal. And on the other hand, reaction time studies often make the assumption that people are just using one strategy at a time, which we know from observing kids and listening to them isn't always the case.
Right.
So there's a real value in bringing these two perspectives together, these two methodologies together, to get a more complete picture.
Yeah. And actually, I think there were some of those early reaction time studies that, really strongly supported this idea that kids were mostly using the MIN strategy. But then when you look at observational studies, kids weren't actually using it as often as those reaction time studies would predict.
Right.
So it really shows you the value of looking at both sides of the coin.
Yeah.
So give us some examples of, studies that have combined those two approaches.
Okay, yes. So, for example, Svensson back in '75, he actually did a study where he repeated that Groen and Parkman reaction time experiment that we were talking about, but he also had the kids tell him how they solved each problem.
Oh.
And he found that while the min variable did seem to explain some of the differences in reaction times, the kids' explanations showed that they were also using other strategies, like using those tie facts that they knew instantly, or using 10 as a reference point. And so those other strategies helped to explain some of the variation that the min model alone couldn't account for.
Okay, so it was a richer picture.
Right. And then in '85, he looked at university students, and he found that the min variable, that was a really good predictor of reaction times for the problems that the students said they retrieved from memory with certainty. However, it didn't do such a good job of predicting for those smaller addend problems because they were probably just doing mental counting on those. The sum2 variable, on the other hand, was a better predictor for the problems where the sum was 10 or greater. So it suggests that even when retrieval is the main approach, different kinds of problems might be processed in slightly different ways.
Right.
And then Siegler's 1987 study, this one really emphasizes that, if you just take all the reaction times and average them together, regardless of how someone solved the problem, you get a distorted view.
Right.
But when he looked at the reaction times specifically for the trials where a child said they used a certain strategy, whether it was min or counting all the numbers or breaking the problem down, the predictions became much more accurate. So it really shows the importance of knowing what strategy someone's using when you're looking at their reaction time data.
Yeah.
And Geary and Wiley, they actually did a study with adults using that combined approach as well. And what they found is that even among university students, retrieval wasn't the only method being used. Oh, wow.
Yeah. Counting and decomposition, those were still being used, especially for problems involving the number 9. And actually, they found that errors were more common when people were using those non-retrieval strategies. And then, in contrast, the older adults in their study, they relied almost exclusively on retrieval.
Okay.
And Lefebvre and her colleagues in '96, they also found that the problem size effect for adults seemed a lot bigger when they didn't consider the fact that people were still occasionally using those other strategies. And when they just focused on the reaction times for the problems where people said they were retrieving the answer directly from memory, that problem size effect was reduced, although it didn't disappear completely.
And Geary's work in 1990 with children with learning disabilities, this is another example of how that combined approach can be really helpful. He found that those children, they tended to have more variable counting speeds and less systematic reaction time patterns when they were retrieving answers compared to typically developing children. So, the main takeaway from all of this is that assuming that everyone's using the same strategy all the time, that's going to lead to a misinterpretation of the data.
Right.
And this combined approach gives us a much richer and more accurate view of what's happening.
Yeah. And I really like this quote from Delaney and colleagues where they say, "We need models that accommodate strategy change and strategy variation and the independent speed up of each strategy."
Yeah.
And I think that really captures the essence of why this combined approach is so valuable. And that idea of speed up of strategies leads us into the last part of our discussion, which is automaticity.
Automaticity.
And this is something we often think about as, when a skill just becomes effortless and fast, like tying your shoes, or, hopefully for most adults, knowing that 3 + 5 = 8 without even having to think about it.
Right.
But it turns out it's a bit more nuanced than that when we're talking about learning addition.
Oh, okay.
So automaticity is usually described in 2 ways. The first is a shift from needing to pay a lot of attention to being able to perform the task without much conscious effort.
Right.
And the second is this speeding up of performance that often follows what's called a power function,
Okay.
which means basically the more you practice, the faster you get, but the rate of improvement slows down over time. So while the moving on process definitely involves our addition skills getting faster, to say it's all about automatization, that's kind of too simple of an explanation.
Okay, why is that?
Well, Chang in '85 made a really important point. He argued that sometimes what looks like automatic improvement is actually just a change in how we're approaching the task.
Oh, okay.
So, for example, moving from counting all to counting on,
Okay.
that is a more efficient way of doing the same thing, but it doesn't necessarily mean you're using less mental effort.
Right.
And also, the typical model of how skills become automatic, like the one described by Anderson, is that you learn the set of steps, and then those steps become more procedural and less conscious.
Right.
So think about learning to drive a car.
Right.
But with addition, it's often the opposite. We start with a more step-by-step procedural approach like counting, and then we move towards just knowing the answer, which feels more like recalling a fact, which is called the declarative process.
Oh, okay.
There's this kind of interesting mismatch.
Right. Yeah, and actually, research has suggested that even when we're retrieving basic addition facts, it's not fully automatic in the sense of being completely effortless and unconscious. And, once you start, you can't stop it.
Like studies have shown that, we can start to retrieve an answer without intending to, but we can often still stop that process. So it seems like retrieving basic facts, it kind of falls along the spectrum from being more controlled and attention demanding to being more automatic with lots of practice.
Okay, so what do you think future research should focus on to really understand all of this?
Well, I think that this combined approach where you first figure out what strategy someone's using and then you look at their reaction times, I think that's really key for future work.
So we need to understand how those individual strategies, whether it's counting or retrieval or breaking down the problem or using rules, how do those become more automatic? And, as Delaney and colleagues found, it seems like that power law of practice applies to the speed up of individual strategies, not just to our overall ability to do addition. And, by looking at those reaction times specifically when someone's using a certain strategy, we can start to tease apart whether the improvement is because the core process is getting faster, like they're counting faster, or whether it's because they're getting better at setting up a problem in their mind and getting to that point where they can do the calculation more quickly.
Well, this has been such a fascinating discussion. It's amazing how something that seems so simple on the surface, simple addition, is actually so complex when you start to really dig into it.
Yeah.
We've seen how there's this dynamic process where kids are trying out different strategies. They're gradually moving towards those more efficient ones, and they're building up this network of memorized answers. And that reaction time data really gives us, those clues about how memory is organized and how we access.